and welcome to 18-3, where we're going to be talking about solubility equilibrium. In this section, we're going to take a look at what we typically call insoluble salts, meaning those substances that do not dissolve, or at least to the naked eye. Well, as it turns out, they do dissolve to a very, very, very small extent, and so we're going to be doing calculations to show you how little they dissolve. All right? But the first thing we want to talk about is something what's called heterogeneous equilibrium. The prefix hetero means different. So a heterogeneous equilibrium is going to be equilibria. Of course, equilibria is plural for equilibrium. It is equilibria that involves different states of matter. All right? So what do we mean by this? Well, if you look at this particular reaction below, you have water, which is in the liquid phase, and you have the hydrogen and oxygen that are released in the gaseous phase. So anytime you have different states of matter, it's going to be a heterogeneous equilibrium. And the deal is you treat this almost identical to any other equilibrium. If you calculate KEQ, it's going to be the products raised to their coefficients powers divided by the reactants raised to their coefficients powers. All right. However, there's something that's interesting here because when you're dealing with a concentration of pure water, well, the concentration of a pure substance in the liquid of the solid phase does not change. And so that value, which is actually tied to its density, is going to remain constant. So if we rewrite this as hydrogen squared times the oxygen raised to the first power, I'm going to change this over to red just to show the difference here. So this one is what we're looking at. This water concentration is not going to change, so we're just going to call it a constant, C. And so since this is constant, we can wrap it up with the equilibrium constant KEQ. If we multiply both sides of the equation by C, multiply this by C, these terms divide out, and now a constant times a constant is simply a constant. So now, let's rewrite this over here. We're going to still call it KEQ. That is going to equal, let's go back to our blue here, that is going to equal our hydrogen concentration squared times the oxygen concentration. And so all you have to do when you're dealing with heterogeneous equilibrium is simply change the solids and the liquids into ones. That's it. Because they don't change, in fact they end up dividing out. This of course would become a 1 once it's divided out, but you don't have to write that in the final equation. So just change solids and liquids to ones and write it just like any other equilibrium expression. So let's go ahead and try this down here. Let's reverse the reaction now, where you have hydrogen and oxygen forming water. KEQ is going to equal this raised to its coefficients power, but it's a liquid, so we're just going to call that 1 divided by the hydrogen squared times the oxygen, both in the denominator there. All right. In the next one down, we have solid phosphorus pentachloride in equilibrium with solid phosphorus trichloride and chlorine gas. So in this case, KEQ will simply equal this, which is just a 1, times this divided by this, which is just a 1, so it's simply going to be the chlorine concentration. That is it. If you want to pause this, you can finish up the last two on your own, and then we can get back together. Alright, so let's go ahead and try to finish up these last two here. KEQ is going to equal, well, this is the reaction where we put the sodium metal into water. We typically do this in chemistry A. It fizzles around, sometimes bursts into flames. The solution turns pink because you have the sodium hydroxide solution forming, and you get the gas that comes off as well, which is actually which ignites if you get enough heat from the reaction. So we have the concentration of the sodium hydroxide squared. It is in the expression because it's AQ. That works. Times the hydrogen, which is raised to the first power because there's a 1 out front, divided by the reactants. Both of them are solids or liquids, and so we just turn them into 1s. We just leave them off. So there we go. And lastly, you have solid calcium carbonate decomposing to form solid calcium oxide and carbon dioxide gas. So KEQ in this case will simply equal the CO2 concentration because the others are solids. So there you go. In the next podcast, we're going to take this idea of heterogeneous equilibrium and we're going to apply it to an insoluble salt. We'll see you next time.